Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to lecture 29 of the course Marine Renewable Energies Systems Analysis, Design and Development. Let us now move to the final stage of energy conversion within a hydraulic PTO system, the hydraulic motors and generators. Up to this point, we have seen how wave motion is converted into hydraulic pressure using cylinders and pistons, and how accumulators store and smooth the hydraulic energy. The next step is to convert this hydraulic energy into electricity. This conversion occurs through two major components, the hydraulic motor and the electrical generator. Let us first understand the role of the hydraulic motor. A hydraulic motor receives a pressurized hydraulic fluid. From the accumulators and control valves. As the high pressure fluid enters the motor, it applies force on the internal rotating elements, causing the motor shaft to rotate. In simple terms, the hydraulic motor converts hydraulic energy into mechanical rotational energy. You may think of it as the reverse of hydraulic pump. While a pump converts mechanical energy into fluid pressure, a hydraulic motor converts a fluid pressure back into mechanical rotation. Once rotational motion is generated, the rotating shaft is connected to an electrical generator. The generator then converts this mechanical rotational energy into electrical energy through the principle of electromagnetic induction. Thus, the overall energy conversion pathway becomes wave energy to mechanical motion, then to hydraulic pressure, then to rotational motion, then finally to electrical energy. The schematic shown in the center of this slide illustrates this complete sequence. Pressurized hydraulic fluid enters the hydraulic motor. Hydraulic motor produces rotational power. Then rotary power drives the electrical generator. Then the generator produces electrical output that can be supplied to electrical loads or integrated into the grid. An important feature shown in this slide is the flexible coupling located between the hydraulic motor and the generator. This coupling performs a very important engineering function. Wave induced motion is naturally irregular and variable. As a result, the hydraulic motor speed may fluctuate continuously. The flexible coupling helps isolate these speed variations and mechanical vibrations, protecting the generator from excessive loading and improving reliability. Now, let us discuss one of the greatest advantage of hydraulic PTO system. Notice the statement on the right side. The hydraulic motor decouples wave motion from the generator speed. This is extremely important. In a direct mechanical transmission system, the generator speed depends strongly on the wave motion. However, in a hydraulic PTO system, energy can first be stored and regulated through accumulators and valves. As a result, hydraulic motor can operate closer to its optimal operating condition even when the incoming waves are irregular. This allows the generator to produce a much smoother and more controllable electrical output. The advantages highlighted on the slide can therefore be summarized as follows. First, hydraulic PTO systems are controlled, allow controlled electrical output because hydraulic pressure and flow can be regulated before reaching the generator. Second, the system can maintain relatively stable generator operation despite fluctuating wave conditions. The third, hydraulic motors are highly reliable and robust components that have been extensively used in industrial and marine applications. Fourth, they improve overall power quality and reducing fluctuations in electrical generation. The key benefits are hydraulic motor help protect generators from shock loads and pressure spikes. They improve system reliability and longevity. They enable generators to operate near their desired speed, thereby increasing efficiency. And finally, they perform effectively under highly variable and irregular ocean wave conditions. Therefore, the hydraulic motor and generator together form the final energy conversion stage of a hydraulic PTO system. They transform a regulated hydraulic energy into stable and useful electrical power suitable for practical applications. In summary, the hydraulic motors convert fluid pressure into rotational mechanical energy. Generators convert that rotational energy into electricity, and the combination provides one of the most controllable and reliable power conversion pathways currently used in wave energy technology. Now that we have understood the working principles and major components of hydraulic PTO systems, let us summarize the key advantages and discuss why they have become one of the most widely adopted PTO technologies in wave energy conversion. The first major advantage is high force transmission capability. Then ocean waves can generate very large forces, particularly in offshore environments. Hydraulic systems are naturally suited for transmitting these forces efficiently because hydraulic fluid can carry large amount of power through relatively compact components. The next is good energy smoothing capacity. As we discussed while studying hydraulic accumulators, wave energy is inherently irregular. Hydraulic systems can temporarily store excess energy and release it when required, thereby reducing fluctuations in power output and improving generator stability. The third advantage is that hydraulic PTO systems are well suited for large offshore systems. Large wave energy converters often experience significant structural motions and loading. Hydraulic cylinders, accumulators, and motor can handle these large scale forces effectively, making them suitable for utility scale offshore developments or deployments. Another important advantage is flexible control strategies. Using control valves, variable displacement motors and modern control algorithms, hydraulic PTO systems can regulate flow rate, pressure and power extraction. This allows the PTO to operate efficiently under varying sea conditions. The fifth advantage is their adaptability in irregular waves. Unlike simple mechanical transmission systems, hydraulic PTOs can accommodate continuously changing wave amplitudes and frequencies while maintaining relatively stable operation. Let us look at some of the applications. One of the most well known application is the Pelamis wave energy converter, where hydraulic cylinders located at the articulated joints generated hydraulic power that was converted into electricity. Another example is the buoy type floating wave energy converter, or bean type floating wave energy converter, BFWEC, developed by Chandrasekaran and Sricharan in the year 2020 and 21, which also employed hydraulic energy conversion concepts for wave power extraction. Hydraulic PTO systems are also widely used in offshore attenuators, where relative motion between floating segments is converted into hydraulic power. In addition, many large floating wave energy devices utilize hydraulic PTO technology because of its robustness and ability to handle high loads. Therefore, hydraulic PTO systems have become popular because they combine high force capability, energy storage, controllability and adaptability within a single power generation framework. Summary: hydraulic PTO technology offers excellent force transmission, effective power smoothing, flexible control and reliable operation under irregular sea states, making it one of the leading PTO technologies for modern wave energy. While hydraulic PTO systems offer several important advantages, they also induce a number of technical and operational challenges. Understanding these limitations is essential for engineers when selecting and designing wave energy conversion systems. Let us first discuss the technical challenges. The first challenge is the hydraulic leakage. Hydraulic systems operate under high fluid pressures and rely on the seals to prevent fluid loss. Over time, seals can degrade because of cyclic loading, wear, temperature variations and exposure to harsh marine environments. Even small leakages can reduce system efficiency by lowering the available hydraulic pressure. In offshore applications, hydraulic fluid leakage may also create environmental concerns, making leakage prevention a critical design consideration. The second challenge involved involves hydraulic losses. Although hydraulic systems are efficient, they are not loss free. As hydraulic fluid flows through pipes, walls, fittings and motors, pressure drops occur due to friction and flow resistance. Every pressure drop represents a loss of useful energy. As a result, not all the hydraulic power generated by the cylinders ultimately reaches the generator. Minimizing these losses is therefore an important objective in hydraulic PTO design. Another challenge is the requirement for complex control systems. Unlike simple mechanical PTO systems, hydraulic PTOs consist of multiple interacting components including cylinders, accumulators, valves, motors and generators. These components must operate in a coordinated manner. Advanced control strategies are often required to optimize power extraction under changing sea conditions. While these control systems improve performance, they also increase system complexity and cost. So, let us now go to the operational challenges. One of the most significant concern is high maintenance requirements. Hydraulic systems contain numerous components that require periodic inspection and servicing. These include seals, valves and hydraulic motors, accumulators, filters and piping systems. Regular maintenance is necessary to ensure reliable long-term operation. The challenge becomes greater in offshore environments. So, this brings us to the issue of offshore accessibility. Unlike land based equipment, offshore wave energy converters are often located far from the shore and exposed to harsh weather environmental conditions. Accessing these devices for repair or maintenance may require specialized vessels, favorable weather windows and trained personnel. Consequently, maintenance operations can be expensive and time consuming. Another important issue is downtime. Whenever a PTO system is taken offline, for maintenance or repair, power generation stops. Frequent downtime can significantly reduce annual energy production and negatively affect project economics. So, finally, we must consider reliability concerns. Hydraulic PTO systems contain many interconnected components. Each additional component introduces a potential failure point. A malfunction in a seal, valve, accumulator, hydraulic motor or control system can affect overall performance. Therefore, ensuring long-term reliability is one of the most important design challenges in hydraulic PTO technology. Despite these limitations, hydraulic PTO systems are remain widely used because their advantages in energy smoothing, controlling and large force transmission often outweigh these challenges. Modern research continues to focus on improving sealing technologies, reducing hydraulic losses, developing smarter control systems and enhancing components reliability. In summary, the major limitations of hydraulic PTO systems include leakage, hydraulic losses, system complexity, maintenance requirements, offshore accessibility, challenges and reliability concerns. Addressing these issues is essential for achieving economically viable and long lasting wave energy conversion system. Let us now look at one of the most famous examples of a hydraulic PTO system used in wave energy conversion, the Pelamis device. Pelamis wave energy converter. The Pelamis device was one of the earliest large scale offshore wave energy converters to successfully demonstrate the practical application of hydraulic PTO technology. Pelamis belongs to a class of wave energy converters known as attenuators. Unlike point observers that move mainly in the vertical direction, attenuators are long floating structures aligned approximately parallel to the incoming wave direction. As ocean waves travel along the device, the different sections of the structure experience different motions. This creates relative motion between the connected segments, which is shown in the figure. That Pelamis device consists of a multiple cylindrical sections like this, connected through articulated joints. As waves pass along the structure, these joints continuously bend and rotate, resulting relative motion becomes the primary source of energy extraction. Now, let us examine how hydraulic PTO system works. At each articulated joints, here hydraulic cylinders are installed. At each joint, hydraulic cylinders are installed. When adjacent sections move relative to one another, the hydraulic cylinders are either extended or compressed. This motion generates high pressure hydraulic fluid. The pressurized fluid is then directed to accumulators where energy can be temporarily stored and smooth. After regulation through the hydraulic systems, the fluid drives hydraulic motors, which in turn electrical generators. The detailed schematic shown on the right side includes the various parts of the hydraulic cylinders. This Pelamis hydraulic PTO system. You can see the hydraulic cylinders, high pressure accumulators, motor generator set, reservoir, and there is a hinge and a generator set. Together, these components form a complete hydraulic energy conversion system. One of the most important engineering achievements of Pelamis was demonstrated that hydraulic PTO systems could be used for large scale offshore energy extraction by Ross Henderson in 2005. The hydraulic approach allowed the device to handle large forces, accommodate irregular wave motions, and produce relatively stable electrical output despite changing the sea conditions. Pelamis therefore became a landmark technology in the development of modern wave energy converters, although commercial deployment forced economic challenges. The engineering concepts developed through Pelamis significantly influenced later generations of hydraulic PTO systems. Let us now examine another practical application of hydraulic PTO technology, namely buoy type bean shaped floating wave energy converter, developed by Chandrasekaran and Srinivasan in the year 2021. This case study demonstrates how hydraulic PTO systems can be effectively integrated into multi-body floating wave energy converters. The BF WEC consists of a central buoy surrounded by a bean shaped floating elements. There is a central buoy surrounded by a bean shaped floating buoys. As wave propagate through the device, the central buoy and the surrounding floats experience different motions. This relative motion between the floating bodies becomes the source of energy extraction. The first important contribution of the hydraulic PTO system is that it converts relative motion into useful electrical power. Instead of directly connecting the moving bodies to generator, the device uses hydraulic power transmission to efficiently capture the transfer energy. The PTO system consists of several key components. These include double acting hydraulic cylinders, hydraulic accumulators, a hydraulic motor, and electrical generator. Together, these components create a complete energy conversion chain from wave motion to electricity generation. Let us briefly understand how this process works. As wave causes the floating bodies to move relative to each other, the hydraulic cylinders undergoes extension and compression. These cylinder motions generated pressurized hydraulic fluid. The pressurized fluid is then stored and regulated using hydraulic accumulators. After pressure regulation, the fluid drives a hydraulic motor and which rotates an electrical generator to produce electricity. One of the most significant findings from this research was the high pressure accumulator. As we discussed earlier, ocean waves are highly irregular. Without energy storage, large fluctuation would occur in the hydraulic pressure and power output. The accumulators act as an energy buffer state. An important outcome of the study was demonstration of hydrodynamic conversion efficiency approximately 25%. This result clearly showed that hydraulic PTO systems can effectively harvest wave energy while maintaining stable operation under realistic wave conditions. Therefore, this study highlights several important advantages of hydraulic PTO systems, including efficient force transmission, energy buffering through accumulators, controllable damping characteristics, and reliable operation under irregular wave conditions. In summary, BF-WEC case study demonstrates how hydraulic PTO technology can successfully convert relative motion between the floating bodies into electrical power while providing stability, controllability, and efficient energy capture in wave energy applications. Now that we have studied both mechanical systems and hydraulic systems, let us compare the both. This comparison helps us understand where each technology performs well and why different wave energy converters adopt different PTO solutions. Let us begin with the energy conversion mechanism. Mechanical PTO systems use direct mechanical transmission elements such as the gears, rack pinion, crank slider mechanisms, whereas hydraulic PTO uses hydraulic cylinders, accumulators, hydraulic motors and generator. And the force transmission is moderate, whereas high force capability is possible in case of hydraulic PTO. Hydraulic PTO systems excel in transmitting large forces because of hydraulic fluids can operate under very high pressure. Then energy smoothing. Mechanical PTO systems have limited capability, whereas accumulators smooth power fluctuation at greater extent. Since wave energy is highly irregular, accumulators, hydraulic PTO systems, accumulators store excess energy under this condition. And when it comes to system complexity, mechanical PTO systems are relatively simple. They involve familiar components such as gears, shafts, bearings and couplings. Then hydraulic PTO systems are considerably more complex because they require cylinders, valves, accumulators, hydraulic motors and fluid circuits and advanced control systems. This complexity also influences maintenance requirements. Then mechanical systems require routine maintenance of gears, bearings and other parts. Hydraulic systems generally require higher maintenance because seals, valves, hoses, hydraulic fluids and accumulators must be maintained regularly. Another important consideration is leakage risk. Mechanical PTO systems have negligible leakage concerns, whereas hydraulic PTO systems always carry some risk of leakage of hydraulic fluid. Then when it comes to control flexibility, mechanical PTO systems often limited control options, and because energy is transmitted directly through mechanical linkages, hydraulic PTO systems provide excellent controllability by adjusting valve settings, pressure levels and hydraulic damping. When it comes to reliability, mechanical systems often benefit from having fewer components and therefore fewer potential failure points. Hydraulic systems can achieve good reliability, but their long term performance depends heavily on the durability of hydraulic components and the quality of maintenance practices. Finally, let us consider a typical applications. Mechanical PTO systems are commonly used in prototype devices educational systems and mechanical energy converters. Hydraulic PTOs are widely used in commercial scale offshore devices such as Pelamis and BF WEC. Therefore, we can summarize this comparison by saying that mechanical PTO systems are simple, easy and easy to maintain and highly robust, whereas hydraulic PTO systems provide superior force transmission, better power smoothing and greater control flexibility, making them particularly suitable for large scale offshore wave energy applications. The choice between these techniques ultimately depends on the design objectives and operating environmental maintenance, then the desired energy capture performance. Having discussed the advantages and limitations and practical applications of hydraulic PTO systems, let us now look at some of important current research trends in advanced PTO technology. Researchers would around the world are continuously working to improve energy capture, efficiency, reliability, controllability and grid integration of wave energy converters. The first major research direction is optimal PTO control. The objective here is to capture maximum energy and by continuously adjusting PTO parameters according to incoming wave conditions instead of operating at fixed settings. The PTO system is dynamically tuned in real time to extract the maximum possible energy from waves. The second one is adaptive damping systems. Wave conditions change constantly and a damping level that is optimal for one sea state may not be suitable for another. Adopting damping systems automatically modify PTO resistances and hydraulic damping characteristics to maintain high energy capture efficiency under varying ocean conditions. Another important one is development in the case of direct drive linear generators. In these systems, the oscillatory motion of the buoy is converted directly into the electricity without the need for gearboxes, hydraulic circuits or mechanical transmissions. Eliminating intermediate stages reduces losses and simplifies the overall energy conversion chain. Then researchers are also exploring hybrid hydraulic electrical PTOs. Then these systems combine the energy smoothing capabilities of hydraulic accumulators with high efficiency of modern electrical generators and power electronics. The goal is to achieve both a stable power output and efficient energy conversion. A rapidly growing research area in AI based control and digital twin technology, where artificial intelligence algorithms can predict future wave conditions, optimize PTO operations and improve energy capture. Digital twins, which are virtual replicas of real devices, allow engineers to monitor performances, predict failures and optimize maintenance strategies in real time. Finally, there is increasing interest in energy storage integration. So, let us now summarize the key concepts discussed in this lecture on hydraulic power takeoff system. We began by understanding why advanced PTO technologies are required in wave energy converters. While mechanical PTO systems are simple and robust, hydraulic PTO systems provide better force transmission and improved controllability and smoother power output under irregular wave conditions. We then studied the basic working principle of hydraulic PTO system. In this process, wave induced motion drives hydraulic cylinders and pistons, creating pressurized fluid. This hydraulic energy is then transmitted through the hydraulic circuit to a hydraulic motor, which drives electrical generator to produce electricity. Next, we examined the major components of a hydraulic PTO systems, including hydraulic cylinders, pistons, accumulators, control valves, hydraulic motors and generators, and discussed in the role played by each component in the energy conversion chain. And we have also learned the hydraulic cylinders are particularly suitable for wave energy applications because they can handle the large forces and low frequency oscillatory motion efficiently. A key component in the is the hydraulic accumulator, which acts as an energy buffer. And we then studied the major advantages of hydraulic PTO systems, then compared the benefits of both mechanical PTO systems and hydraulic PTO systems. Finally, the current research trends are also discussed related to improving the hydraulic PTO systems. So, in the next lecture, we will move on to another important PTO strategy technology used in wave energy converters and continue our study of advanced energy conversion systems. And these are the key references cited in this lecture. Thank you for the interest. Thank you.